Problem 21.7. The question is to consider the problem of optimizing this objective function subject to the three constraints here. So optimizing that means that we're either trying to minimize it or trying to maximize it. Okay, and the question says that the point x star satisfies the KKT. And now there are two questions actually. First one is that if this x star satisfies the KKT, the question is, does it satisfy the first order necessary condition for minimization or maximization? What are the KKT multipliers? The second question is, does this x star satisfy the second order sufficient condition? Okay, so as you can see in this case, since we don't know if we were minimizing it or maximizing it, we have to try both of them. If we're trying to minimize it, then the objective function is just this. The three constraints are this. This is constraint functions. I should say this will be our f of x if we're minimizing it. Otherwise, the f of x should be equal to negative of this to the sum. And the g1 of x is just I need to take the negative sign, so it becomes less than or equal to 0. And also g2 of x is x1 plus x2 minus 2 less than or equal to 0. And g3x is equal to negative x1, that is less than or equal to 0. Okay, so we form the Lagrange function g1, g2, g3, then multiply them by mu1, mu2, mu3. And then we take the KKT, which gives us this as the gradient with respect to x. These three are just the original inequality constraint. These are the non-negativity constraint for the KKT multipliers. These three are the complete slack completeness condition. Or yeah, so that's that's three conditions. And then solve this. You will see that. Oh, sorry, not solving this. It says that x star equals to 0, it satisfies this KKT. So you just say that now x equal to 0 satisfies this, and see what are the mu1, mu2, mu3, and we got this. But that's not possible because this contradicts with this. Okay, so that means this is not even possible. The 0, in this case, 0 cannot be cannot satisfy the KKT condition in any way. So that means if we're trying to minimize it, then 0 cannot be a KKT point. Okay, so now we ditch this case. We try the maximizing it instead. So if we're trying to maximize the objective function, the only thing changes is that the f becomes negative f, or the f is actually this. And we do the same, exactly the same procedure. This is G1, G2, and G3, and then we have the mu1, mu2, mu3 multiplied to them. And the KKT condition is this, gradient of L with respect to, gradient L with respect to x1, x2, and the three inequality constraints, the negativity constraints, and then the three conditions like this. And then we try to solve it, and we'll have these three values, which are okay now, okay? Because they are indeed greater than or equal to 0. So in this case, you can see that these are the three constraints. Apparently, when you plug in 0, 0, the first one is active, it's equal to 0. Second one is inactive, so this one is not. The third one is active, so this one are active. G1, G2 are active, and their corresponding mu's are positive. So in this case, we're going to see if the point is the point 0, 0 is a regular point. We just need to get this matrix, a Jacobian matrix. It's a gradient of G1, gradient of G3 that gives us this. At the point 0, we can actually evaluate it, because in this case, this will be just 0. And then we got that. So this is the full rank matrix. This full rank matrix means that x is indeed a regular point. So it is a regular point, and x equal to 0 is x0 is a regular point. And also this, together with x equal to 0, satisfies this bunch of things. So that means the x equal to 0 is indeed a KKT condition for maximization. Okay. Well, second question is for maximization. What is that? Does it satisfy the first order necessary condition? And what is the what are the KKT multipliers. Okay, so as you can see, if we're maximizing it, then everything becomes reasonable. The f is this, g is this, and what well, I'm thinking I just skipped to the third question already, because the second question is already answered in this one. The KKT multipliers is just these are just the KKT multipliers. So this is actually number 3. So this 1, 2 is already solved together above. Okay, so so that is the problem. And to see the second order sufficient condition, we need to check the Hessians, right? The f gradient f is this, Hessian will be that. Gradient of G1, Hessian of G1, gradient of G3, Hessian of G3. Remember that because mu2 equals 0. So when we take the weighted sum of the Hessian, like this one, this is anyway gone because mu2 is equal to 0. So you plug in those 3 Hessians, and you have their corresponding values, 2 and 4, and eventually you get this. So this is the Hessian that we're if we're going to check the second order sufficient condition, we just need to figure out this T tilde space. Remember that T tilde space is the Jacobian of the G1, G2, G1, G3, because they are active and their corresponding mu's are positive. So the G1, G2, we already compute them, and at 0, we form this matrix, which is this. Okay, and the null space of this matrix, apparently this matrix is 2 by 2 full rank, so it's invertible. The null space will be just the single 0 vector. Okay, so that means if you're going to choose any y from this T tilde, the only choice is y equals 0. Then you multiply that to both sides. Well, you don't need to do that anymore. Sorry, you don't need to do that anymore. You cannot find any non-zero vector from this set. So there's no way for us to check if this y transpose y thing is greater than 0 for non-zero y, because the only choice for y is equal to 0. So this means that the second order sufficient condition is actually satisfied. It's just trivially satisfied, because you don't even need to worry about there's no non-zero vectors from this T tilde. So it is satisfied, trivially satisfied in this case. Well, to look at the problem from more, geometric interpretation, is that we are trying to find the minimizer of this function right here, or maximizing it, I should say, maximizing it under these 3 conditions. So let's look at what are the 3 conditions. Remember, keep in mind that this is the x1 squared minus x2 less than or equal to 0. This is less than or equal to 0. This is less than or equal to 0. So I draw the picture below, right here. This is the x1 minus x2 equal to 0, right? So this is just a quadratic. X1 minus squared minus x2 less than or equal to 0 means the x1 squared less than or equal to x2. That means x2 is greater than or equal to x1 squared, so that means this area. Okay, so this is the first constraint, the point the solution must be living on here. Okay, second one is x1 plus x2 minus 2 less than or equal to 0, so that should be this area, because this line is x1 plus x2 equal to 2. And the last one is x1 is greater than or equal to 0, so it should be this area. Okay, so you take the intersection of the 3, you get this piece of triangle. Look like a triangle, it's not exactly a triangle. But anyway, now look at the objective function. I write the objective function right here as x1 minus 1 squared plus x2 minus, x1 minus 2, x2 minus 1 squared. So we're trying to maximize it. And you can see that this function is actually kind of a parabola or a bowl shape. So it reaches 0, it takes the value 0 at this point, and it just go like circles. So imagine that you have a ball facing yourself, and it touching the 0 at the center. Okay, it's popping up the screen. And as you can imagine that the maximum value, because it's getting larger and larger value. So you can see that the maximum value, if you restrict yourself to this area, the maximum value is here. So in this case, we actually can see that it's local maximizer. It is a local maximizer.